little connection with yesterday for but we will find a connection maybe tomorrow. Okay, so today I will do something different, but still let me just recap a little bit what I did. Okay, so what I said yesterday, that you can have a Hamiltonian which is I don't have to specify what the Hamiltonian is, and it has only a degrees of, at each Hamiltonian in 1D, and so you have a one-dimensional system, and each place you have a site variable called Ni, and Ni can take values, let us say 1, 2, whatever, so q values, some q finite values. Okay, so for these kind of systems, we just know that whatever the Hamiltonian and whatever the energy, we write probability of a configuration of the system. This we write, so there is q to the power L configurations. So probability of a configuration is e to the power minus beta e of c, okay, divided by this partition function, and then partition function, that's the partition function. Okay, and then when it is, if you can write it is in terms of transfer matrix, then it is e to the power minus beta e of c divided by trace of t to the power L. Okay, trace of t to the power L. And what I was talking about is that if you have a configuration, a given configuration which is some Ni, then let us, for example, let us say 1, 2, 3, 2, 2, 1 something. So if this is your configuration, this is equivalent to that. So this is your configuration, and then what you do is that each configuration you can represent by a matrix product by replacing the variable Ni by the corresponding matrix Di. Okay, so this configuration you first replace it by a matrix product, so D of Ni. Okay, and then you call it product over I. So these are I sites, and each site you have some variable. So corresponding variable, if it is 1, you call it D1, whatever, and you are trying to write this function as if it is something like that. Okay, so what we are writing is that probability of a configuration is equal to trace of this one divided by trace of t to the power L, where t equal to summation over I d Ni. Okay, all summation over n dn n equal to 1 to q. Okay, so right, I mean that's the one. So then t to the power L actually tells you, just because it's a matrix product, so this is this sum. If you make a product, then configuration cell D1, 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 D1. So basically it will count all the configurations. Okay, so trace of each term here is a configuration. This is sum of probability of all configurations, and this is the probability of the particular configuration you are interested in. Okay, so that's the way you want to try to write it. Okay, so that makes, it's a very useful way of writing it, because any joint probability or any correlation function or anything you want to calculate, it would be very easy. For example, if you want some D1 at some point, and D1 means 1 at some point, and a distance r, at a distance r you have another 1 or maybe another 2, doesn't matter what you want to write. So let us say what is the joint probability of having 1 here and a distance r 2 here. So for example 1 I and 2 I plus r. Okay, so this one can be written as, at these two places the matrices, all other places you can put anything. Okay, so all configurations having 1 at site, let us say first site, and in a distance r you have 2, and anywhere else, so corresponding matrix you write D1, and anything is basically T. Okay, this matrix T. So this is T to the power r minus 1, and then this is D2, trace of that divided by trace of T to the power L. This is very simple. Any correlation function you can write it like that. Okay, there is T to the power L minus r minus 1, T to the power L minus r minus 1. Okay, so all the matrices in total, always there has to be L. Okay, so that's the way you write. But then writing like that, it is nice here, but then you can actually do it in a diagonal basis of, right, diagonal representation of D. So this function, so D1, D, all D's in the diagonal basis, D goes to D tilde, that is Dn goes, that is U inverse Du. Okay, that is the diagonal basis, and all T's can be now replaced by by the diagonal matrix. Okay. So basically this, if the if the eigenvalues of T are just if the eigenvalues of T are just lambda 1, which is greater than lambda 2, greater than equal to lambda 3, like that, assuming that T is a symmetric matrix, all eigenvalues are real at this stage, and there is a strict distinct eigenvalue lambda 1, which is the largest. Okay, so that is given by Perron-Frobenius theorem, which we discussed. Okay, so if this is the situation, and then whatever the dimension of the transform matrix, lambda d, okay, greater than equal to lambda d. So if these are the eigenvalues, so you have a matrix lambda which is in all diagonal elements are lambda 1, lambda 2, like lambda d, whatever the dimension. So if this is your lambda, then this one can also be written as this equal to trace of, so d becomes d1 tilde, this is just lambda to the power r minus 1, just replace it, d2 lambda to the power l minus r minus 1, this is the one, divided by trace of lambda to the power l. Okay, so this is in a new basis. Okay, so that's the matrix we write down. Okay, so then what you can find is that the lambda to the power l, all the matrix element here is lambda to the power l. So this one to the large, so this one, the denominator is just lambda 1 to the power l when l goes to infinity, and then here also you have a term lambda to the power l minus r minus 1, lambda 1 to the power this. Okay, so if you take it out, the first element here is 1, so this matrix goes to 1 0 0 0, everywhere 0. If you just pull out this one, l to the power lambda minus 1, so you take it lambda 1 to the power l minus r minus, this is lambda 1 to the power l minus r minus 1, and then the whatever the matrix remain is this matrix, let us call it A. So this is just, this matrix is just 1 1. Okay, so from here it remains 1 1. So let us write it a little clearly, so that let us do it again. So you have d1 tilde, trace of d1 tilde, and lambda 1 to the power r minus 1, I will keep it like that. So this is lambda 1 to the power r minus 1, and this is d2 tilde, I think tilde is missing here, lambda to the power r minus 1 is just, this is just lambda 1 to the power l minus 1, so I'll take this one out, lambda 1 to the power l minus r minus 1, I take it out, and here this is just 1 1. Okay, and this 1 1, and then below you have lambda 1 to the power l. Okay, so now what happens is that if within the trace this one becomes just 1 1, so this is just becomes 1 1 element of this matrix, 1 and 1 element of that divided by lambda 1 to the power l, and lambda 1 to the power l cancels with that. Okay, lambda, and then r minus 1 is there. So if you multiply this with this matrix, the first term, because r dependence will cancel out. Okay, in the first element, the second element is just lambda 2 by lambda 1 to the power r, that's the only r dependence will remain there. Okay, so if you multiply the whole thing, you get a constant plus some lambda 2 divided by lambda 1 whole to the power r. Okay, so that's what you get. Somebody, one of them asked me questions later, what will happen instead of trace if you have a different, if you have an open boundary situation, right? I mean, this is a periodic boundary condition, you have a trace. In an open boundary condition, this trace will be replaced by, let us say, replace this one by some other vectors, whatever the vectors represent your, this boundary, and this one will be represented by whatever boundary. So for example, you can say that this one is always 1, this doesn't change its state, and this one is always 2 or 3, whatever you want. Okay, so then this is the matrix, it becomes this matrix, and the rest of the argument just goes through, right? I mean, so it's instead of trace, you just get it, you get some matrix element, but this term is just a constant plus lambda 2 by lambda 1 to the power r. So the correlation, this function always goes exponential. Okay, because lambda 2 is strictly less than 1. Okay, so this kind of formulation, so this is the general formulation of whatever the problem. So now question is that this will work only when you know these d's. Okay, so I just give you an example where transfer matrix in Ising model, where you have a transfer matrix. So you have a problem, now we are specifying, you have a Hamiltonian, and let us say that you have a transfer matrix. Okay, if you have a transfer matrix, so this is the transfer matrix, then your dk can be written as this transfer matrix kk. Okay, so summation over k dk is of course t, because summation over this is just identity. Okay, so dk can be taken like that, and then it works. The whole procedure works. Calculations are pretty simple. And so now, question that at this stage again I'm just emphasizing that if you know the transfer matrix anyway, you know the solution. It is only a nice cute way of doing things, but the utility is missing here. Okay, so we will come back to that later, right? In other classes, why this is useful and how we use it. Okay, so today I'll go to the other side. Yeah, any questions on this?
First day you gave example of copper and iron oxide. There we may not have Hamiltonian of this kind, usual kind, but still we can apply this method to that.
Copper and why do you say that copper and you don't have a Hamiltonian?
1, 0 you can take everything.
Yeah, so because this is two. When you say 1, 2, 3. Just name, right? If I replace it saying that A, B, C, D, E, things still fine. Until now it is fine. This one you don't, right? You have to think from the Hamiltonian how to get a transfer matrix. But the formulation is perfectly fine for any.
There will be a Hamiltonian.
Yeah.
Copper will interact with a different energy than zinc.
Yeah.
Or whatever it is.
Yeah.
So you put in those
Details.
details and you simplify it, becomes an Ising model. Becomes exactly that.
Yeah. If you.
In general, an Ising model in the field.
Yeah. We can start that. Yeah.
Yes, but it's instructive to do it.
Yeah. I think the Huang still has some sections on this. Huang has some section on this, so you can read that part. Okay. So other thing I just wanted to point out. That this is the way I connect what I will talk today. So basically, when I talk of a Hamiltonian, directly you are writing what is the probability of finding a configuration C in stationary state. That you are writing directly. You are not involving the system to find it out. Okay. So this is you are taking this information from some other source, Boltzmann, and that works. Okay. So now question is in some situations you may not know this, and then you have to calculate this, and we today will try to see how to calculate this, right? If you do not know, if you have a rule-based dynamics, how to calculate this. Okay, so that's what we try to do. Okay, so I think I will just start with an example. Okay, let us there are teachers. So let us play a game. Okay, so let us say that in a playground you have 3 circles, one named at 1, 2, and 3. Okay, and what you want to do is that you ask the kid, your teacher is, let us say, here, and everybody has to face the teacher, and then it decides which one is left, right. For everybody, what is left, right. If you are pointing somewhere. So what you do is that for one, so what you want to do is that ask a student to sit, stand somewhere, and with a dice. Okay, and if the dice is 3 and 5, okay, so then you go to left. If the dice gives you 3 and 5, you go to left, or if it is anything else, you go to right. Okay, so basically that is meaning I'm just talking of probability 1/3 and 2/3. That's the dice gives you that. So basically you are going to right. So similarly 2, you go to right with probability that, and with left you go to, so this is left and this is you go to right. Okay, and similarly from 3 you go to right with probability. Sorry, I think this is left. Okay. So now for this guy, right, right is this way, so you go like that. From here, right is this way, so you go like this. This is 2/3 actually. Somewhere I'm saying 2/3, and for here this is right, so you go like that. This is also 2/3. Okay, so from here you can go to 2/3, and this one is 1/3. Okay, so this is also 2/3, and this is 1/3. Okay, this is 1/3. From here to here it is 1/3. From here to here it is 1/3. Okay, so that's it's clear. So if it is 1, you go to right with probability this, and left with this, left with 1 third. 1 means 1 third. This is 1 third. Okay. This 1 arrow means 1 third. 2 arrow means 2 third. Okay. So that's the game. So now let us say that you have many of such things are drawn, and you have some 100 kids which are n kids which are playing this game on the field. Okay. So you start everybody, let us say to start with, they are in circle 1. Everybody is standing circle 1. That's where you start the game. And when you raise your hand, they throw a dice, go somewhere. Okay. And they keep doing that. Okay. So now that's the game, and you want to know what will at a given very long time, what will happen to this, right? How many people on the average will be in circle 1, how many will be circle 2, how many will be circle 3, something like that. You can write, this is the kind of question you want to ask. Okay. This one, so the problem, what I'm aiming at, right? You have 3 configurations, right? You can call these are 3 configurations, and you are moving among the configuration within some rules. Rules I have, narrate the rules. Given this, eventually the question which I'm asking has an answer. Some fraction of kids will be there, some other fraction will be here, and some other, and the sum will be of course the total number of kids. Nobody is sleeping. Okay, so that's the situation. Okay, so now let us say that initially I do not know the initial situation, but generally at a given time, let us say what is happening. Okay, so those which are at 1, how is it? So some number of people, some number of kids are at 1, so I call it n1. Okay, so similarly n2 and n3 at a time t. Okay, so now I'm saying that in next instant, like this delta t, what I'm saying, so in next instant how this n1 will change, right? N1 means number of students at this, how it will change. Those which are at n1, they might go to 2 and 3, right? And those which are at 2 or 3 might come here. That's the way it will change. So there is those which will come, that's the gain to this one. So delta n1, this equal to, okay. So so let us, this is a general example, but let us say that the probability that the delta n1, that those which are at n2, okay, from n2. So let us say this 2 to 1, I call it some W2 to 1. Okay, some number is there, but I will write it generally. So delta n1 is that from 2 and 3 it can come. So 2 to 1. Okay, so n2, those which are at 2, of them some fraction will come because they are doing with probability. So W2 to 1 plus n3 W3 to 1. It's not only this term. What are the other terms? Some people will also go minus n1 W1 to 2 plus n minus n1 W1 to 3. Okay, so this is the term. Okay, so this number, if the number of things, so similarly I can write an equation for n2 and an equation for n3. Okay, so now if I if the number of kids are very large, okay, so this is then I can say that the total number of kids is that n equal to n1 plus n2 plus n3 any time, and this is, let us say, very large. You have a large number of people, so then I can divide it by n, and I can divide it by n, total number of n, and divide it by n. So divide it by n, divided by n, and divided by n. Okay. So other thing which I missed here, I talk when I describe this problem, I talk the probabilities, right? 2/3 probability is going here, 1/3 probability is going here. Okay, and so this one, in the game also you have somebody has to raise hand when they have to toss the coin. So there is a time also involved. Okay, so instead of saying that these are the probabilities, it is good to say these are rates. You can define some rates, right? So in a general problem, if you are in configuration 1, from 1 to 2, you go with some rate. Okay, so these are the rates. So W, so I'm just now defining W12 is the rate. Is the rate from rate of moving from 1 to 2. Okay, so this is the rate. So if this is the rate, the probability is just rate times dt, right? That's the probability. So I just said that this by this and this times dt. There is also dt here. Okay, dt. So W1 to 2 dt and W1 to 2 dt. Okay, so that's the probability. So probability of moving, but if I divide it by n, delta n by n, this one, right, this is a fraction of people or students at 1, okay. So this can also be, if I divide it n, so that is 1, okay. So this n1 by n, so the n1 by n I call it p1, n1 by n, so I call it p1 plus p2 plus p3, okay. And this sum is of course 1, and this can be thought as the probability if n is very large, okay. So this equation can be written as, and the dt delta t, this is delta t can come here. So this is basically, this one can be called probability of p1. So this equation can be written as dp1 by dt equal to, so this is p2 w2 to 1 plus p1 p3 w3 to 1 minus p1 w2 to 1, no, w1 to 2 plus w1 to 3, okay. So that's the equation, okay. Is okay with everybody? This is fine. So the probabilities are, so just they're evolving, probabilities evolve with this kind of equation, okay. So it's not one equation, there will be other equations. Can you quickly tell me the other ones? dp2 by dt, okay. p1, you can come from 1 to 2, so p1 w 1 to 2 plus p2 p3 w3 to 2 minus p2 w2 to 1 w2 to 1, okay. So w2 to 1 and plus w2 to 3, okay. So these are that is also another equation. So these equations can be written as a matrix, right? I mean a matrix format. So how do I do that? Just write that. So d by dt. So let us write the equation d by dt of p1 p2 p3. Of course the sum has to be 1. So this equal to, what is the diagonal element? This one, right? When from p1, this is the diagonal element, right? So w1, whatever it goes away, this is with a minus sign. That comes with a minus sign, because the diagonal means from 1 you can go, right? I mean whatever you are just looking at change. So this is just minus w1 to 2 plus w1 to 3. That's the diagonal one, right? And from here, from wherever you come to 1, okay. So this is, right, I mean from p2 you can come. So p2 you can come w2 to 1, okay. So and this one is w3 to 1. Similarly this one is, you want to come to p2 from 1, so w1 to 2, and this is minus of w2 to 3 plus w2 to 1, okay. So this is the one, and the third one. So the third one is w, you want to come to 2, 3 from 3 to 2, okay. So this is the gain term. So these terms are gain terms. So whatever you get here, these are gain terms, and this is the, this is the loss term. So the diagonal contains all the loss terms, okay. So the now w3 to no, sorry, you want to come to 3. So this is w1 to 3, and this is w2 to 3, and this is w3 and w3. So w3 to minus of w3 to 1 plus w3 to 2, right? From 3 wherever you can go, you go, right? I mean that's in the diagonal term. So this equation, so now there is a matrix, okay, fine. So let us write this matrix. So what are the elements of the matrix, okay? Okay, so this times p1 p2 p3, okay. So that's the equation. Okay, so now what are the elements of the matrix? So let us say that what are the elements of the matrix, okay. So if I say for a general configuration, so for 1, so what are these elements? Can I write the matrix element? Okay, so you can see that 2 to 1, right? I mean, usually if you call a matrix M, this is 1 1, this is 1 2, okay. So M I J, so this is the matrix elements of this one, So if I call it, I write an equation dp by dt equal to mp. Okay, p is now a vector, 3 by 3 vector. So now what I do is that, what is the matrix? If this is M, what is the elements, matrix elements? Okay, so Mij is just, I mean, if I not equal to j, so 1 2, this is M1 2, so Wj to I, this is equal to Wj to I. That's the matrix element, right? Mij if I not equal to j, so this is just that. Okay, 1 2 is that, this is 1 3, so that's the Wi to j. And what is Mii? Mii is that summation over j. So so from I wherever you can go. So summation over j not equal to I, okay, minus and Wi to wherever you go j. Okay, the whole sum is there. So let us keep this matrix here and proceed further. Okay, so now, so this equation what I am writing here. So now if you want to think of, instead of, no, we will not solve this problem, and now you can solve this problem, right? I mean, so do you know how to solve this problem? Do you know a solution to this problem? What is the solution? P is a function of t, of course, dp by dt, t of t. So what is the solution? Yes. So basically this is m of p of t. So this actually gives you solution p of t equal to e to the power mt, mt, tm, p of 0, p at t equal to 0, p at t equal to 0. Okay. So if you know p at t equal to 0, you just get this one. So now do you know how to calculate this again? E to the power lambda t, e to the power t m p t, right? I mean, how to, this you know how to calculate, right? I mean, just go to the eigenbasis, it will, you can write it. So the way to do it is that just write pt in terms of the, so pt is a vector, it can be written in terms of eigenvector of m. So there is the eigenvector of m equal to some e1, e2 and e3, if these are the eigenvectors of m. So write pt equal to 0, so that is p0 equal to some c1 e1 plus c2 e2 c3 e3. Okay, so you know that if this is the situation, so you can write this equation. Any vector can be written as the eigenvector of this. I'm changing the notation, two different notation I'm using. This is a vector, this is also a vector. I can also write like that. Okay. So now, if you write, so can you find this CG? So basically, if you know the matrix M, the matrix M contains only the rates. Okay. So if you know the matrix, of course you can diagonalize it, get the eigenvectors. So you know this one, and this one. These three things you know. P0 is your initial condition. Like, I say that everybody is trained in 1. So what is your initial condition? 1 0 0. Right? I mean, the probability is 1 here. Other two places it is 0. You can start half here, half there, whatever initial condition you want to start. You can put that initial condition here. So this side is known, this side is known, this side is known, and this is 3 equations, right? I mean, because this is a vector. So you can solve this C1, C2, C3. Okay. So that is basically this one you can find out, right? I mean, this one can be find out, from the initial condition and knowing the matrix M, and M is coming from the dynamics. Okay. Are the eigenvectors M? E1, E2, E3 are the eigenvector M with same thing, lambda 1, lambda 2, lambda 3, 3 eigenvalues. Okay. So M gives you these eigenvectors and eigenvalues, that is given. So you can calculate, right? I mean, because M is known. When you define the problem, M is known, right? I mean, M is known, you know this, so C1, C2, C3 you can find out. So once you find that out, you put it here, right? I mean, so this is equal to e to the power t m, and then this is times C0, but then M operating on E1 will just give you lambda 1, right? So e to the power t m of lambda 1, m becomes lambda 1, okay? So pt equal to 0. So this equal to e to the power lambda 1 t, okay, e to the power lambda 1 t C1 E1 plus C2 e to the power lambda 2t plus C3 e to the power lambda 3t. Okay. So, that is your PT, because this e to the power m operating on E1 will this make this lambda 1. Okay. So, this is just the solution. Simple. So, this is the way to solve it, but let us look at what will be the general situation. Okay. So, okay, we will go to the other side. Yes. So that will come later, like how it will look like, and whether one of them has to be 0, and that we will come back. Huh?
We are expanding P0 in terms of E1 into E3.
Yes.
It is possible only when they are linearly independent or orthogonal. Is it possible that always they are?
Yeah, yeah. Yes. Orthogonality would. Yeah.
Otherwise, you cannot write like that.
No, you cannot write like that, but it is always there. Yeah.
Complete set.
It's a complete set. Yeah.
For all W1.
Yeah. So this has certain properties. I have not written the general one.
As long as the matrix is diagonalizable, this is true.
Yeah.
Can happen. But probably this is always diagonalizable.
Yeah, no, but if
All the elements are non-zero, it is certainly diagonalizable. They don't even, it doesn't have to be symmetric. This
That's
can be
good.
proved.
Yeah.
You can prove a number of things, including the fact that all eigenvalues are of Einstein,
Right.
except one is zero.
Right.
so, this can be. So this will. Yeah. So the matrix has certain properties which were.
Some of the W's are 0, then what is the state?
Then it's possible.
Reducibility.
The matrix cannot be diagonalized. I mean, like it's upper triangular. But even so, it's a valid matrix, and you can. I mean, you will go to an absorbing state.
Yes. Yeah, yeah.
But those are exceptional situations.
So right, if you have only off diagonal element, for example, like the one, then you cannot go to the other side, right? you cannot go to certain setup. So if you, right,
So that's anyway like your dynamics.
it's a ergodicity.
Right.
Yeah. So it's not it's not cover. So if you want to cover all the full phase space, it will not right. All the elements. Some element 0 is fine. I think when some elements are 0, then the condition is probably reducibility. Right, if it is right, if it is irreducible, then it is yeah. And if it is not irreducible, I am making a statement. So if it is reducible, you can always get it. That's fine. If it is not reducible, then you will suffer the ergodicity. If it is reduced, I mean, yeah, no, I will also like it. But I am just saying that for his question, he will suffer. No, because you will have an observing state, like there is no ergodicity, it will be broken.
That's what
Yeah. Suffer basically means that you don't have evolution, you go and stop somewhere. If the matrix is reducible, you will stop somewhere, right? Okay? And so because the phase space will have sectors, right?
A good reference for this is the book by Van Kamp.
Yeah.
One compact chapter discusses all of the properties very well. He gives the proofs also, which are not hard. But,
Yeah. Okay. So we'll do it for the general one. Okay. So let us see that what will be the term. This is the same thing. I'm just for the sake of completeness, instead of 3, right? For example, in Ising model, the number of configurations is 2 to the power L, right? And any configuration to any configuration, in principle, you could have gone, but the dynamics which we use is only a single spin flip dynamic. So some rates are 0.
most are 0.
Most of them 0. Yeah, most of them are 0 because you just generally cannot go to any configuration to any other configuration. But it's still connected. If you think it is a graph 1 to 1 to 1, it's connected, and each one is also reversible, right? That was in the first lecture I talked about that. So if you have many configurations, like many configurations like that. So what are the situations you have? Like you can go from here to here, and here to here, and maybe here to here, and here to here, like that. Like I cannot draw all of them, but anyway. So let us that. So here to here is, let us say, is not allowed. Okay, that is not there. But I'm just saying that whenever you connect from here to here, there is also a rate. You come back from here to here. Right? Everything is doubly connected. That's a requirement of equilibrium.
When you say
not allowed in one time step. We are okay, right? I mean, in the rule, it is not there. In the rule, the Monte Carlo or the Metropolis algorithm, it is not there, right? I mean, it's a single flip. You are using trial configuration as a single flip. In that situation, you will some rates will be there, some rates will not be there. But I'm saying that firstly, the all points has to be connected, okay? And whenever there is a connection between 2 points, there has to be doubly connected for the detailed balance to be satisfied. Because if you go like that, if one of them is 0, then you cannot satisfy. So this kind of graph has to be doubly connected. Everything is connected, and of course doubly connected. That's the minimum requirement. You still do not know whether it's a detailed balance, but it's a minimal thing. So the graph must be looking like that. Okay, is it clear? So this I show at some point in the one. So this is the kind of configuration you have, and once you have a configuration like that, ergodicity in long time limit is guaranteed, right? Right? I mean, you start from anywhere, you can reach anywhere, right? I mean, because they are doubly connected. I mean, you just and all points are there. So as long as all points are there and each of them is doubly connected, you go wherever you want, right? I mean, just follow the links. So these are the conditions on ergodicity. So this is so now what you have is that whatever rates are there, they are some jump in configuration. So each rate is some, this is C, general configuration, and let us say this is C prime. So this rate is W C to C prime, and this rate, this reverse one, is W C prime to C. Right? I mean, this is the transition rates. Okay. So these are the rates. There, you have corresponding probabilities with W dt. And if you write this equation, this will exactly look like that. Okay. So all the rates are given. Okay. For Ising model, you derive the rate using, right? This, from the Hamiltonian. That's where you need a Hamiltonian. But we can start here saying that whatever the rate I give, like this example I gave, right? I mean, this is a game. So in this game, what will happen, right? I mean, I can all kind, whatever question I ask, I can do it here. So now, so the equation will like dpc by dt for single one for a given configuration. So what is happening to a given configuration? So let us say this configuration. Okay. So I make it little more. Let us say this doubly connected, like it's coming here and going there also. So the configuration C can be come from many other configurations, right? I mean, you can come from many other configuration to C, and so basically those will give you a gain term. So this is summation over all C prime. Okay, W C prime, any other C prime to C, because that will give you a gain term. Okay, minus summation over C, W C prime to C, but you have to have P C prime, probability that you are there, and transition rate. Okay, and then there is a loss, because from the same configuration you might go to somewhere else. Okay, so that is P of C, W C to some C prime, and the sum is always C prime. Okay, I mean, this don't, if you don't want, these are dummy indices, you can put it C double prime also, it's okay. Okay, so but you are going from PC, this C and this C are the same. Okay, so this term, this equation can be written in terms of matrix form, right? I mean, and the matrix elements are that. Okay, so the matrix elements are also given there. Okay, so this can be written as, the whole set of equation can be written as dp by dt. Okay, this is the configuration probability, of the system being in one configuration C. So dp, and this is the full vector. Okay, dp by dt equal to mp. Okay, m is this matrix. So what is again, to complete? So again, matrix element mij. So what is the dimension of this matrix? For example, in Ising model, if there is two variables at each side, it's a one-dimensional system. What is the dimension? 2 to the power L. Okay, so this is 2 to the power L by 2 to the power L. It's a huge matrix. It's not that simple. Okay, so the mij, the ij element is this probability. So the W mij is just W Cj to Ci. I mean, Mij is W Cj to Ci, and the whatever I written. So Mii. So this is I not equal to j, and I equal to j Mii. So this is Mii equal to just W Ci going to Cj summation over j with a minus sign. Okay. So all configuration from whatever you call ith configuration. This is the This is the elements. Okay. So now so does it remind you any other equations? This calculations, where else you have done this calculation? This kind of calculations? Huh? Yes, in a Schrodinger equation. For example, if you have a Hamiltonian, like you have a two-level system, h equal to sigma z, and you have an initial state, initial wave function psi. Okay, so the whatever Hamiltonian you have, just I h cross del psi by del t equal to h psi. Okay, so you put a Hamiltonian here, and then this is the same kind of equation, except that these factors are missing here. Okay, and this I is a very important factor. So and the other difference, this is exactly like a Schrodinger equation. The other difference is that you are evolving the probability directly. Okay, so what you are evolving here, the amplitude. Okay, so as far the evolution go, the evolutions are similar. Okay, I mean only thing is that to find probability at the end, here you have to take a mod square. Here just as such the probability is conserved. Okay.
One question, in this general setting you can also have terms like W1 to 1, right, in principle?
No, but I am changing delta p, delta n. So that term is not there.
Oh, I see.
That term is not there.
You're saying that won't change it.
Yes. So W1 to yeah. So you can put the numbers, whatever your numbers you have. Okay. We will not do that particular one. So this is one that this is kind of the solution of this is as hard or as easy as Schrodinger equation, because as far as the evolution goes, it's the same evolution, it's the same kind of equation, linear equation. Okay. Okay. So now let us see some properties of matrix M. Okay. So now if something is evolving like that, and as I say that if you want that the system, the probability do not evolve any further, like the stationary state basically means, so the stationary state means that probability becomes independent of time, right? I mean P star, let us say this is called a stationary state. So P star C will not depend on time anymore. Okay. So the time actually goes away. Okay. So if you wait sufficiently long, the fraction of times you find the system in a configuration, like here, number of kids in a fraction of kids in circle 2, it is just a number, right? I mean if you wait for large time, so that is the probability. Okay, and that is not evolving any further with time. There is a limit. Okay, so that limit, if you want that probability here, this is the time evolution, right? I mean you have t here and you have a t here. That's the way it is evolving. Okay, but then very long time, t goes to infinity, you know that this will not evolve in time. So if it doesn't have to evolve in time, then you want that dp by dt equal to 0, right? So if this is stationarity. So stationarity is given by p dp by dt equal to, stationarity is just some p star c. So in the stationary condition, so dp by dt has to be 0. Okay. So now if this is 0, then that means mp is 0. Right. So that means that mp equal to 0, but I can also write 0p, right? So which means that m, if you want stationarity, m should have a 0 eigenvalue. So so that's the point. So if I can prove that m has a 0 eigenvalue, then I can prove that doesn't matter what you write, it will go to a stationary state. Okay. Okay, so look at this one. Can anybody tell me whether if the one of the eigenvalue of this system will be 0? This matrix. It can't be? No, he finds it here. Okay. Eigenvalue, how to write so okay, what is the determinant of this matrix? If the eigenvalue is 0, determinant has to be 0, right? Can you now reduce this question? The determinant of this matrix is 0. Okay, okay, so I'm just saying that look at the column, okay? So 3 to 1, 3 to 2, 3 to 1, 3 to 2. This column sum is 0. This column sum is also 0. This column sum is also 0, okay? Right? Why it is happening? Because every time you go from one configuration to the other, let's say 3 to 1, 3 is giving you 3 to 1, 3 you will lose, but at the same time 1 will gain, right? So every arrow is contributing twice. Once positive contribution to 3, or maybe negative contribution to 3, positive contribution to 1. So that's the way. So things balancing out. Here you are going from 3 to 1, 3 to 2, but then same thing when you go to from 3 you are losing those. Okay. So every arrow contribute twice, one with positive, one with negative. So the sum in this way has to be 0. And if you take this matrix element, you take a column sum, you can also show it, right? The matrix elements are written, just make a column sum, you will get it 0. Okay, so and you can see that it is 0 here. Okay, that's the reason I kept this small example in front of you. I'm not erasing that. Okay.
It's easy to write the left eigenvector. Yeah, because just of what you said. So
Yeah. If you take a left eigenvector, yeah. If you just put 1, 1, 1, that's also 0. Yeah. Yeah. Right, yeah. Yes. That's not a trivial, yeah, okay. Yeah, but that doesn't have a meaning, yeah. So this P is the one which you want. So okay, so you can see that because the column sum is 0, and but now if the column sum is 0, the determinant has to be 0. What is the argument? Because if you are calculating determinant, the row can be replaced by the column, and if you have everywhere 0 here, then of course the determinant has to be 0. Okay, so the determinant is 0. That tells you that one eigenvalue is 0, at least one. Okay, at least one. Okay, so
in fact also at most one. I mean that can be uniqueness.
no, not from the statement that
not from the determinant is 0.
But from the properties of the stochastic matrix.
No, if you consider only ergodicity, otherwise you can have two, right? If you have a graph like that, then it is, right? If you have a graph like this, and this, it will go here, and this, and then this is go here, like and there is no outlet from two different things. So there can be multiple, right? So I'm not complete. So yeah. If you have multiple, yeah. If it is ergodic, yeah.
If it can be diagonalized.
Yeah. If it can be diagonalized, yeah. Okay. So if it is ergodic, then it can be proven that it's at most one eigenvalue is 0. Okay, and that is the largest. It also can be proved that, is there a simple proof for that? The most largest eigenvalue. This is the largest. So there is an eigenvalue. So all I'm saying is the determinant. So what we get from this is the determinant. One condition we get the determinant of m equal to 0.
it's clear that all the eigenvalues can be 0 or negative, because otherwise your probabilities will go up.
No, that is a reverse argument. So from the matrix, can you prove it? One can prove it, but the proof is not that simple. So I'm not going.
It's not a 10-minute proof. It's about half an hour.
Okay, so I skip that. Yeah. Yeah. So I'm just saying that some properties I'm giving it here, which can be stated in 2-3 minutes. Other properties you have to read from Van Kampen, and you accept me that kind of the matrix satisfy those properties. Okay.
Actually,
so
most practitioners just accept it.
Yeah. It is.
Yeah.
Yeah. So basically there is a matrix M and determinant of M equal to 0. That tells me that at least one eigenvalue has to be 0. Actually there is only one eigenvalue is 0 if it is ergodic. That's a statement. So and 0 is the largest. 0 eigenvalue value 0, eigenvalue 0, statement 1 it exists. Okay, that means determinant is 0. Second is it's unique. That's what we find, and this is we did not prove, but so one can prove.
It's unique given it's ergodic.
Yeah, given it is ergodic.
And it's a finite matrix.
Oh yeah. Okay.
finite ergodic matrix. Yeah, finite.
Because we saw an example of ergodicity breaking in the Ising model, for example, right? If I take the 2D Ising model and take the limit, then of course it's ergodic, but ultimately.
Yeah, but that is an infinity matrix eventually.
Yeah.
Yeah.
But in some limiting sense, it has to.
Yeah, so there is actually a next eigenvalue
Which
will give you the time scale.
Exactly. Yeah, because these are relaxations.
That's right.
Yeah. Okay. So I think if I'll maybe I can elaborate on a little bit on this point, this 2D Ising model, right? Yesterday I talked about phase transition cannot happen in 1D short range systems. Okay, so that is based on Perron-Frobenius theorem. Okay, and I stated the. So, but you see that in 2 dimension it can happen. Okay, so what exactly is happening? Which part of the Perron-Frobenius theorem is breaking down in 2D? I mean, when Perron-Frobenius theorem breaks down, it doesn't say anything. It just doesn't apply. It cannot say whether there is a transition or not. But at least you have to break it to have a phase transition. I mean, there is no way. So which one is breaking down? Finite. Okay. Because the finiteness. Because if you want to take a Ising model like this, so you have you have this lattice, but then you said that this is M and this is, let us say, L. So now there are spins here. So which means that you can think of this is one vector which is translating like that. Okay. So then this one, the dimension of this is 2 to the power m, because each one can be plus or minus. Okay. So there are 2 to the power m. So if you want to, if you think it is a transfer matrix, the transfer matrix dimension is 2 to the power m. This m is not that m matrix. So this is 2 to the power m by 2 to the power m. Okay. So that's the matrix. So now as long as m is finite, you still have a finite dimensional transfer matrix, and the Perron-Frobenius theorem applies. But m actually is infinity, right? I mean, you have to take m goes to infinity along with L. Okay. To get the phase transition, right? I mean, so that is the way you break this finite one. Okay. So the dimension of the matrix become infinity. Then, I mean, those are difficult animals to handle. Infinity matrices. Okay. Generally. Okay. So one is eigenvalue, about eigenvalue 0, that it exists, that is determinant 0. It is unique, under good conditions. Under good conditions. Okay. I mean, that actually includes most, and mostly we study only those. And third one, that it is largest. Okay, this also I have not given the proof. So if 0 is the largest eigenvalue, that means all other eigenvalues are negative. Okay, at least modulo wise. Okay, so it can be because the matrices are asymmetric. You can have complex eigenvalues, but if it is complex, they must come in pairs because the matrix is real. Okay, complex eigenvalue must come in pairs, and modulo wise, this is the okay. Real part. Yeah. Okay. Yeah. Real part. So real part is negative. Okay. So this is the largest. No, modulo is positive. Yeah. Real of lambdas is less than 0, except, right? I mean, real of lambda except the 0 eigenvalue. Real of all others. Okay. Let us put it in the fourth statement D. Largest and real of lambda, all others. This is less than 0. Okay. So that's the, if it is complex. So this one tells you that, so let us say that the largest, which is 0, lambda 1 is 0. So this term here will just, you can, if the largest eigenvalue, then you take it away. Okay. So this is just 0 because the whole thing goes away. Okay. And the other one are negative. Okay. Less than 0. At least the real is less than 0. So this will, t goes to infinity, this will decay. Okay, and this is also negative, so this will also go to 0. So basically what we left out is that the E1, which is the 0 eigenvalue, okay, sorry, 0 eigenvector, okay, and the 0 eigenvector by definition up to a normalization factor, because up to a normalization factor the 0 eigenvector is the stationary state, which we have shown here. dp by dt equal to 0 means that. Okay, so to find the stationary state of this matrix, given all this.
Can I ask a naive question?
Yeah, please.
Very confused. Suppose I start with an initial condition which has no component over E1, then what does this tell you, that everything decays, or I'm just confused? Let's say I start with an initial condition which has no component over E1. So C1 is 0.
No, you cannot get that. And realize.
But mathematically, there should be just impossible.
Yeah, this is impossible. Yeah.
So any configuration I take, it should have some overlap
With the zero edge. Yeah.
Because when you say you take a configuration, what you take is a column vector in which the elements are positive.
Yes, strictly. Yeah.
Oh, that's also
The other thing you can do from
Yeah.
some of these things is that the
So right, if you
sum of probabilities is conserved.
conserve, but if sum of the probability is 0, for example, for the time being, you can say that some of them are 0 in the stationary state.
the fact that the things are constrained to be positive.
Yes. Yes. No, but I'm just saying that if even you can if you think that is it possible to have sum of the eigenvalues 0, sorry, sum of the column entries in the initially they can be 0, but stationary state.
Oh, in the stationary.
It is not possible because those will throw away the things, right? Because these are you are calling stationary probability. Some probability at 0 means those are never visited, right? So it is not possible. So you will have all of them non-zero, right? In the stationarity. Yes. Yeah. So I'm just saying that tells you that the zero eigenvector, if the one which you are looking for, has all entries which is positive, strictly greater than 0. Okay. So that's the point. You can never have. There's no way to do that. Yeah. Okay. So that's the general thing which I talked about. So now, given all this information, right? We'll now restrict ourselves only to finding the stationary state. What is P star? MP equal to 0P. I call it P star. When this happens, then it's just this the eigenstate. So what I need to find, if P star is your stationary value, then MP star this equal to 0. So you need to find a vector for which this equation. This is a linear equation, MP equal to 0. Okay. Right? So this matrix, all you have to solve is that this times P1, P2, P3 equal to 0. Find P1, P2, P3. Yeah. If in 3 by 3 case, if I just put numbers, whatever 2/3, 1/3, so this equal to 0 is a simple equation, right? And this inverse doesn't take right. So you have to solve it. So the inverse doesn't exist means that one of the thing you cannot solve because of the 0 eigenvalue. But that is up to normalization. P1, P2, P3, what you get, you have to normalize it at the end. So you get the weights, but you have to normalize it later. Okay. So all of them you cannot solve. So right, one will remain, but that is normalization eventually. Okay. So MP equal to 0. That's the kind of equation you want to solve. Okay. But then such equations are difficult in general because this is not so simple as 3 by 3. Right? It is 2 to the power L by 2 to the power L, and in general you are talking of a thermodynamic system. So that's not a feasible situation.
But because the matrix is hard, it is computationally not that.
Yeah, even 2 to the power. Very difficult.
Because the dimension is growing.
2 to the power 100. How big is 2 to the power 100, right? Small, right? If you have to do computation, right? Here he talked about a Ising model of 16 by 16, 256. 2 to the power 256 is like 10 to the power 100 about, na? Because you divide it by 3. 10 to the power 100. 10 to the power 100 is very big number, right? 10 to the power 100 is cannot be. I think more than 10 factorial is not just cannot be computable in. Right, in terms of integers, right? This is not possible.
It's not computable, it's also not imaginable.
Yeah. It's not imaginable. 10 to the power 200 is probably a number which you cannot count. Nothing in this world counts to that.
That's why you do statistical physics.
Yeah. So it is not possible to do that. 10 to the power 100 is not imaginable because the whole universe I saw in terms of meters is 10 to the power minus 24 to 10 to the power plus 24. That's all. 24 zeros, you see, right? You are talking of hundreds. Don't imagine. There is nothing will count that. Even the total number of quarks in the whole universe will not be that.
The number of bosons in the universe is 10 raised to 89.
Look at this.
The number of fermions is 10 to the 80. Just trivia.
No. Basically,
Where did you get that from?
Weber.
anyway.
This is on the internet, it's on mainly photons.
Okay. So I think I will not do this problem like, you know, you know everything and you can do it. This is very simple. Okay, so we'll actually go to a more interesting problem, which is where there is the non-equilibrium and actually 2 to the power. It's more than that, not 2 to the power L. It's actually infinity space. Okay, so we try to solve a problem like that, a general, nice problem.
Lambda 1 is equal to 0 and lambda 2 and lambda 3, it is mandatory condition, it is negative.
Yes. Yeah, here written na, largest and real of all others is less than 0. So you have a 0 eigenvalue equal to 0, and that 0 exists, it is unique and it is the largest, right? And then if there are complex eigenvalue, all the real parts has to be negative.
Lambda 2, lambda 3, each tends to 0 fraction 0.1, 0.2, it can be happen.
Fraction. These are numbers, right? What do you mean by fraction?
These are real numbers. It can be irrational even. What is fraction?
No, he is asking they could be very close to 0.
Less than
Not exactly 0.
Oh, they can be close to 0. They can be close to 0.
0.00005 is okay.
Yes, fine.
I
Yeah.
guess it's important to stress then that these lambda 2, lambda 3, they are like inverse relaxation rates.
Yeah, they will determine actually lambda.
Yeah. So okay. So true.
The long time relaxation will be very large.
So maybe you can stress that.
yeah, okay. So as I talked earlier, like I also talked about correlation functions. Where does the correlation function comes from? How does the correlation function come into the picture? Okay, the correlation function comes to the picture from the transfer matrix, right? You have some matrix and you are looking for some correlation function here, and then there I show that it is just lambda 2 divided by lambda max time to the power this. Okay, so this is to the power r log of that. Okay, so here also if one of them is 0, the next one actually tells you the gap, right? The gap from 0. Okay, so this is e to the power this just is a time scale. So basically you can say that if this is much smaller, because this is in the order I have written, so this goes away. So this is t e to the power t lambda 2 t, because it's negative. So you can say that t by tau. So tau is lambda 2 inverse effectively. Okay, so that's the way it is decaying. So if there are a lot of things which are decaying, all of them are decaying. The slowest decay is the one which is closer to 0. Okay, so that will give you eventually, if you want to see time just before reaching the stationary state, how it is evolving, you see only this eigenvector. Okay, close to stationarity you see only that next largest eigenvalue which is closer to 0. Okay, so now we will go to a problem which I describe in details, and I want to just emphasize particularly, I changed the track a little bit. So Arnav actually discussed about Bose-Einstein condensation. So I thought that I will also discuss little bit about condensation, but in real space, not in momentum space. Okay, and this is by some non-equilibrium. We do some non-equilibrium models, and let us look at the model. Okay, so the model is just this. So let us think that you have boxes, many boxes, like like that. Each box can contain some number of particles. You can have any number of particles. Okay, so the box site is called I, and the number of particles in the box I call Ni. Okay, so the value Ni can be now 0 to infinity. Okay, so now the phase space is actually infinity, because each site you have can have any values, and anywhere you have any number of particles. So this is the box. Okay, so and then I'll also use a periodic boundary condition. So this is box size, this is L, and this is 1, they are connected. Okay, so this is L, I equal to L, and I equal to N, L and N connected, because it's on a ring, that kept on a ring. So now so this is, as I said that in the first lecture, modeling basically means that you define the space, you define your variables, and then you have to define a dynamics. Okay, now dynamics or interaction or whatever. So here we define the dynamics directly, not like write a Hamiltonian and derive a dynamics as equation of motion. We tell you the dynamics. Okay, so the dynamics we just have the transfer particle from one box to the other box. Okay, some other box. Okay, and in this case it's a neighboring box. So transfer particle from here to, let us say, here. That's the only thing. Okay, so you transfer one particle from a box. If there are particles, of course, transfer a particle from here to the next box. Okay. So now let us just, I'm asking you, just think about it. So you have some boxes, you have some particles, okay, and then let us say that you are doing completely randomly, okay.
But is this one-way motion?
I'm talking one-way motion. So close your eyes. You have a lot of boxes. Hold one box. Take a particle, drop it to the next one. Just keep doing that. Hold, drop like that. They're on, they're all around you. Just hold it and put it there. Just keep doing it. Okay. Now what do you think will happen? You start with, let us say, all particles in one box, and you start doing that. Just keep doing that. Just whatever comes to your mind, go there, hold, put it to the next one. What will happen?
My head will start spinning.
So what do you think will happen? What will be the average number of boxes and particles in a boxes or whatever? What do you think will happen in this system? Look, for example, if I ask a very specific question, if you initially, let us say that box number 3 has all the particles are here only, okay. So now if t goes to infinity, if you keep doing this, just throw a particle from box to this one, what will happen in large time limit? So number of particles, so this is I and this is, so it will be equal. On the average it will be, so the average number of particles at box I, if you plot as a function of I, this will be flat, okay. So that's the, so now I'll just complicate the dynamics little more. So let us say that instead of doing here, you have a rate which is u of ni, okay, some function. So you first go choose the box and find how many particles are there, and you transfer particles with this rate, okay. Not always you do it with this rate, okay. So now you can be any functions like why u ni. Because you are choosing ith box, from here it is u of ni, from here u of nl, okay. From here if you want to throw to 1, it will be u of nl, and similarly, right, you know what up to. So now there is a function, okay. The function can be anything. So now let us discuss what kind of functions can be. So u of n, okay, u of n versus n. So, and we have many situations. What kind of functions are either decreasing, increasing, maybe constant, approaching something. So we draw all kind of functions. So let us, first one, we say that you draw a decreasing function, okay. So let us say un is a decreasing function. So now can you tell me what will happen?
Also the rate decreases
with n, yeah. If you have lesser particles,
then if I make this thing very big, then it won't go anywhere.
no, but I'm saying that you can start with some arbitrary initial condition, right? This is very typical.
Let's start with this one.
Okay, we'll do it later in the tutorial. So you start with something, okay, some no, because that is a long time, because people will get just wrap up into that circular arguments. No, I don't want that. So there is some arbitrary configuration you start with, okay, and then all you do is that, what does it tell you? That you throw, your throwing ability goes down if the number of particles goes down, right? So now what will happen in this situation? Same, how?
Because more number of particles are there, then we throw it more time.
Yes, okay,
Less number of particles are there, we throw it less time. So
yes,
The other way around. If they are more, then you
throw less.
because even with
If it is more, then you,
yeah.
if you more, you throw less, okay,
promoting clumping.
right? You're promoting, right? If you have more, let us say 40 versus, yeah, yes. So for your answer is that it will remain there if you start like that. So, right?
Start from one, that's an atypical initial. This is what will happen if you start from a typical one.
No, but his proof is that I can start from any.
No, it will happen. You can start happen, it will happen.
I understand.
Yeah, time will be long.
Here it will be easier.
Yeah, I think I'm not doing well. Okay, anyway, so basically this is some configuration you start with, some number of particles somewhere. So if it's a decreasing function, then the result is that eventually some box will just accumulate, because you just do, and those boxes are not evacuating. Big boxes are not evacuating. Small boxes are evacuating faster. So basically, eventually you will get some large box somewhere, you don't know where, but once it you always have. So in this case, you have all particles in one box. So that's your that's your final one. Okay, so here the final one is this, here the final one is that. So,
But are they all there? Or can there be some
there can be some distribution, but effectively most of them are there.
very large fraction?
Very-
will be there? There will be a finite fraction elsewhere.
Yeah. That could be some. So basically this large fraction will be there. So maybe some small thing here and there, but there will be somewhere there is a big one. Okay, so that's the situation. But this the
What is the parameter which is controlling it?
No.
Like you're controlling something.
no. I'm talking of many different situations, and details I'll come later. Okay. So now let us think of a function 2. Second one. Let us say the other one, right? Un is a increasing function of un versus n is an increasing function. So in this case, what do you expect? Here, small boxes do not evacuate, large boxes evacuate very fast. Okay, it will be flat. So this one will be flat. So I'm just saying that this is just flat. Okay. So basically, the stationary state. If you're looking for stationary state for this function, so increasing basically means that n goes to infinity, it goes to infinity. Decreasing means this. So there is another possibility that it is a constant. Okay. So if it is a just constant, nothing will happen, right? If it is just constant, as I say that close your eyes through here, you are just doing it at a constant rate everywhere. Okay. So then it is also flat. Increasing, decreasing, it's and the other one can be flat, right? 3, it's a flat. It's still. A function, if this is this un is just a decreasing, just a constant, then it is a flat. I'm not writing that. So now in this situation, the stationary thing is just flat. Here the stationary thing is just kind of a bump. Okay, so this is different. But if it is going to 0, un going to 0, then you always get this, right? There is no escape, right? So what do we want a situation like a phase transition, right? This clump is like a condensation, right? Some particles are condensating on some side, and this situation it will always happen. This situation will never happen, in all other situations. So I'm just saying that we are constructing a situations where you can go from here to here by tuning some parameter, the one which you are asking. So question that what kind of functions we use. Okay, so of course that it has to be decreasing function, right? And if it goes to a constant. Okay, so a function, a general one is that you probably something which goes like that and reach a constant, something like this. A function like this could work. I don't know whether it will work, but that's a possibility. Okay, so then in these situations you might go from here to here. Okay, and we try to do these calculations in more details using this master equation approach. Okay, so now what we start is that your function. So what you have is that your rate is just un. It can be a function, so I will not specify now, okay? But in my mind, I know that I will not choose this, and probably I will choose something like that, okay? Okay, so these situations I know, and I will choose something like that, and we will do it exactly. Exactly means analytically, right? We can do it to the fullest if the functions are in certain kind, and we will do that. So now. This model, let me name it so that it will be useful to get the references and things like that. So you can see that the particles only go, the rate depends only on the number of particles in the same box, on the departure box. Okay, so this is the 0th box. Like if you say that I plus r or something, this is the 0th box. So you say that this is the range is 0. Okay, so this process in general is called zero range process. Okay, zero range process. Okay, so I use formally GRP. Okay, so this is the model which you want to discuss now onwards is this zero range process, and you can get a lot of references. Just try it out. You get them, and I'll give you some references later. Okay. So the model is clear, right? You have a lot of boxes. They're in, put in a circle or whatever. Periodic boundary condition is there, and you take a particle, throw it only to the right with rate un. Okay, un is not specified at this stage. Okay, and in this situation, that the configurations are infinity. There are huge configurations, and so you still have a master equations here that dp by dt, you can write the master equation dp by dt equal to mp. This is the equation we want to solve, and mp equal to 0 is the equation we solve. So mp, but that is okay. So now let me write it, dpc by dt. Will it be equilibrium system or a non-equilibrium one? If I can solve or whatever. So I'm just saying the asking, will this system have a, will it have a current? If you, yes, right, because it's just always moving in one way. So if you take a cross section, you always find that particles moving only one way. So there will be a current in the system. So generally there is a current in the system. So dpc by dt equal to summation over c minus summation over c pcwc to c prime. Okay, and then there is another term, the gain term is just summation over c prime and p of c prime wc prime to c. Okay, so these are the terms. So dp by dt equal to 0. Basically, you have to balance these equations. Okay, so there are a lot of terms which are negative and there are a lot of terms which are positive. Okay, so if you can smartly balance this, like this sum is actually this sum, then you get the solution. That's the point. One way to do it, by the way. So because this is c prime, you just take it inside. You just say that pc prime w to this to that, this equal to that. Okay, so it's the same c prime. No, one way to do it is that just summation over c prime pc wc to c to c prime minus that plus pc prime wc prime to c. I mean, this is dummy index, but I am forcing it to be same c prime, right? I mean, I can put it here, and then I said that each point is 0.
But that looks like detail balance.
Of course, that is detail balance. That is detail balance. So one way to make this thing vanish is that when this and this actually vanish. In general.
Not in this.
Yeah.
Yeah, because in this case,
It will not be. It will not be. So I'm just saying that in general, master equation, when you write the master equation, then you can, the term is, I'm just defining a task. The task is to make this sum vanishing with this sum. One simple way, in a general situation, one can make these two things vanish when you say that each term here has a corresponding term here, right? I mean, c prime to c. So for every pair of configuration c and c prime, this equation is satisfied. This equal to that, then it will vanish. Okay. So that is one way. Okay. So let us see what are the other things we can think can happen. Okay. So you have a configuration c prime, c. Okay, and you have a c prime, and let us say that you also have other configuration c double prime. Okay, and they are connected. Like so a general situation is that you go from c to c prime. When you go from c to c prime, okay, did I mention that this is a detailed balance? Okay, this condition is already this is detailed balance. Okay, detailed balance. Samik, it is sorry. Okay. Okay, this is a general thing, like when you change a configuration from c to c prime, right? I mean, they go from one configuration to the other, and then there are you have also rates, like there are things like that. So each one has some outward arrows, like c can go to wherever, and c can, right? I mean, the configuration c can be arrived also from many other ones, right? I mean, a configuration C, you can come from many other configuration, and from C also you can go to many. It is quite possible that some of them are also here. It doesn't matter, right? I mean, it is possible also. So now, question is that if in a system, if you think that the number of inward arrows for every configuration, the number of inward arrows are same as the number of outward arrows, there is a possibility that every outward arrow, right? Outward arrow is a negative sign, might balance with some inward arrow. In such situation also things will balance, right? I mean, you have
huge number of ways to
yes, huge number. If you can find one, that is good enough. I mean, huge is fine. Just find one. So I'm just saying, if it is possible, it is. But then you should know this kind of trial is. You should go to that kind of trial only when the number of inward arrows and number of outward arrows are same for every configuration. Then there is a possibility. Otherwise, you keep it even, right? I mean, you cannot do this. So let us make this statement, right? I mean, more. What do we look for? So now, for every config, so let us write that. For every configuration C that goes to C prime, okay, you have there, you find, here it is, you have to find one, you find a C double prime such that probability of C WC to C prime balances with probability of C double prime WC double prime to C. So in the detail balance, so if you are going here, it is balanced by this one.
Maybe instead of saying for every configuration, you should say for every transition.
Every transitions, okay.
Because
Yeah, every transition for every transitions, okay. Every transitions, okay. Yeah, if there is no transition, of course you don't have to consider.
These are time dependent.
No.
oh yeah,
P is the general P, right? It's stationary one. I'm looking for stationary one.
Trying to find the steady state.
I'm find a steady state.
Okay.
dp by dt equal to 0, so there is no time
Trying
difference.
to find, given the rates, some sense of
Some vector which satisfy this dp by dt. Okay, that's what. Yeah.
for W.
Yeah, I think I mentioned that. So basically, the rest of the talk we are restricting only to MP equal to 0. This linear equation you try to solve even when the matrix is large. That's all we try to do. Okay, there are many different techniques. This is one. Okay, so for every transition, right? Whenever a transition, a transition basically some configuration to some other configuration, right? This is pretty general. There is no assumption here. But here, this find is not that you are not very clear whether you can always find. Okay, you may not find. Here it right. You have to look for, and if you know the model or whatever. I do not know how to find. There is no general rule. If you find a C double prime such that C to C prime is balanced by some C double prime to C. Okay, and this find a unique, because this has to be unique. So basically, what I'm saying is that this outward C to C prime is balanced. This one is balanced by this. Okay, and let us say this one is balanced by this, or maybe this one is balanced by that. I don't know. This one is balanced by that. So
use that same one again.
Same one again. You can also choose the same one again. Okay. So for every pair, right? Every time you have a transition, you have a C double prime to balance it. Okay. So if that happens, then also this will be balanced, because for each configuration it is balancing, right? Each, right? Are you with me? Each transition it is balancing. So let us look at this equation in terms of pictures, right? So these -1 are outgoing arrows from a configuration, right? And in that positive ones are incoming arrows to the configurations. And for each configuration, this equation has to be satisfied, which means for corresponding probability, the fluxes has to balance. So for for each transition, if you are doing it, like if you can do that, and you are balancing it this way, then it is balancing anyway. Okay, so that's the configuration, and this is called pairwise balance. Okay. So this requires 3 configuration at a time, right? Not 2. In detail balance, C to C prime to C, right? Here 3. C to C prime is balanced by some C double prime to this. That's the one, and this is called pairwise balance. So basically, one pair is this outgoing, and other pair is this. Okay, so this is pairwise balance.
That seems to be the simplest way to sort of get out of this detailed balance.
Yes. Simplest.
Special case.
Yes.
C double prime equals
But should I? Yeah.
This
But it is introduced. I was introduced by you.
No, we are the.
Yeah. So I think, okay. I think, okay.
There's a paper by Unterschutz, Ramram,
Yeah.
Sahi and myself.
Yeah,
Where
okay.
this-
So that's the first time it was introduced by Mustan. Okay, so this is pairwise balance. So this is very okay. We are also trying some called H balance. No, no.
Tell us later.
Yeah. So this is a pairwise balance condition. So pairwise, if you can, if you find suitably, this is here this suitably, right? It's not true always. Like the master equation true for all kind of dynamics, including equilibrium. Okay. Some dynamics can be satisfied by these kind of conditions by detail balance. Okay, and then the probability measure is actually Boltzmann. Okay, so you can. This is the situation. It's the detail balance, equilibrium, Boltzmann, whatever you get it here. This is a very simple situation. The next simple situation is that in some systems you can use this pairwise balance. So here, the flux balances, but there might be a current in the configurational current in the problem. Okay, and I'm demanding the problem which I'm going to study, or we are going to study together, like this zero-range process. Here one can use pairwise balance, and we'll find it suitably, and it's pretty nice. Okay, so let us do a little bit. No. For any u. In this situation, you can any u would work. Any dimension, not only dimension, any graph. Any graph, it is true. So whatever structure, in that is true. So now what we do is that, second thing, we just make a of course, you know that this is a big matrix, solution is difficult. We make some answers. First thing, this is the general thing which I introduced, which you may not know. So this is called detailed balance. We use this. Okay, this is a side remark. And then second thing, we will also make answers, and which may or may not be true. Eventually, we'll see whether it is true. Okay, so the answers, you just make answers. Answers means is some assumption. To start with, we start with the assumption, and then if it works, it works. If it doesn't, we'll throw. Okay, so just answers. Okay, at this stage we make answers that probability of this configuration Ni. The configuration is given by, if you specify all the values of N1, N2 to NL, the configuration is specified. P of Ni. So this is proportional to product over I, some function of Ni. Okay. Okay, so this is what we want to write, right? So this one has a name. We'll name it later, but let us understand what we are writing. So question that probability, right? Is proportional to f of, let us say this N1 is 1, whatever, 3, 4, 7, 9. P f of 3, f of 4, f of 7, f of 9. Probability is proportional to this for this configuration. Okay. So you have I'm assuming that there exists a function f, right? Such that the probability is given by f of 3, f of 4, f of 7, f of 9, whatever the configuration is. So that's what I'm assuming, but that's not enough. Okay, that's not enough, because I know in my system, if you take a particle and put it somewhere else, the total number of particles is conserved anyway, right? They're not going anywhere. The total number of particles has to be n. So you have a system size n, and that's, let us say, summation over I Ni equal to n, which is conserved. Okay, so this part is conserved. So if it is conserved, then I have to also write to make sure that this, doesn't matter what I write, that condition is satisfied. Summation over Ni has to be n. So that is restricted by putting a delta function, right? If you put summation over I Ni minus n, if you put that, this will take care of the number conservation. Total number of particles is conserved. So this is fine. But still this wiggle thing, because this is just a normalization of probability. I can write this, right? This I can write. If I put a normalization factor here, and normalization can be thought as the inverse of, right? So I can call it divided by Q. Q is the inverse normalization. This is normalization constants. Okay. So what is my Q? This Q now, right? This Q is sum over all of them, right? Sum over all of them. So Q equal to sum over all Ni, and product over I, and f of Ni delta, let us put it brackets, this is 1, and delta summation over I Ni minus n. But of course, you can see that n is a number which is conserved, so the Q must also depend on n. And in the whole system, I equal to 1 to L, let us put the parameters proper, 1 to L. So this is L also is there. Okay, so these are the parameters, because everything else is summed up. And this Ni is just summation over N1, summation over N2, summation over N3. That's the meaning, right? This is the probability of one configuration. Probability of all configuration has to be summed, that has to be made 1, and that's what we are doing by putting this Q. Okay, so Q equal to all configuration. This is summation over, if you write, that's the one. Okay, and then can somebody now, given the statistical mechanics, right? A lot of people have done it differently. How to take care? So this sum, can you do this sum? If this restriction is not, can you do this sum? Yes. How? So let us say this restriction is not there. What is the result? Each sum. Yeah, so f ni to the power ni goes to 0 to 1. So this is just, so if it is not there, the summation over n1 or n1 f of n1 to the, this is just one of them, and there are l of them, so to the power l, right? I mean, to the power l, right? I mean, this is simple. And n1 can be a general one, fn to the power l. So without this restriction, doing this sum is pretty easy. Okay. So now, how to get rid of these restrictions, right? So that is what we know. Like if you have a number which is conserved, right? Number of particles which are conserved in a system, you use some chemical potential, and so those things we know. Okay. So we try to do it in a general one. So what we do is that, let us say that q as a function of n is a very general one, nothing to do with chemical potential, nothing. So let us say a function or any function which is f n you do not know. So one way to find it out, right? If you do not know, is that fn, just write fn is a function of n you do not know. You just say that z to fn z to the power n summation over n. This you call some gz. Okay. Okay. So I'm just saying this is called a generating function. Okay. If you have anybody familiar with this? Okay. Okay. Most people don't. So this is called a generating function. Okay. So if you just write a generating function by definition, then fn is equal to, right? This is just z to the power n fn, right? So basically, so fn is the coefficient, right? Coefficient of z to the power n in in expansion of gz. In the series expansion of gz around z equal to 0. Right. So if you know gz, let us say some function gz, in a you would expand generally like gz equal to something z to the power n summation over n, right? So basically whatever the coefficient of z to the power n, you write it like that. So by definition, this equation tells you that fn by definition is just z to the power n coefficient of z to the power n of gz. That's my notation. This whole word I'm replacing by gz. Okay. So, but you can say that, if you do not know fn, how do you make a sum, right? This is a way to find fn, but you have to know what is gz, right? So to get gz, you have to know fn. So it's like a circular. It looks like you did not do anything, right? What did I do, right? Probably nothing, right? Looks nothing. But in certain situations, you can calculate it. I'm giving you a homework, and that's where probably we'll stop. So let us say that fn is a function which satisfies certain relations. Let us say given to you. So for example, I can give fn equal to 3 fn minus 1 plus 2 fn minus 2. Okay, and this is one example, example A. Okay, so maybe fn equal to fn minus 1 plus fn minus 2. Okay, this is another. Do you know what is this equation? Fibonacci, right? This is Fibonacci. So now question that, let us say that what is the 20th Fibonacci number, or 47th Fibonacci number? That's what you want to calculate. Okay. So what you do is that just take a generating function, and then rest of the calculation you gz equal to just fn. You want to calculate fn, just write fn z to the power n summation over n equal to 0 to infinity. Okay. So n equal to 0 to infinity. Okay. So this is what you call the generating function. Okay. So now use this here. Just make a sum here, summation over n z to the power, both sides you multiply by z to the power n and make a sum. Okay. Then you can see that you get some gz's, right? And you can actually calculate gz without knowing what is fn. So use this, feed it here. This is A and this is B. Okay. So feed it either A or in B, right? These are two different problems. Okay. And find what is gz here. Okay. Who doesn't believe that it can be calculated? The gz can be obtained, right? Right? Just multiply z to the power n and use wherever you find a term like that, you replace it by gz, and both sides just take gz and you can get it. So you get gz, and once you get gz, you find the coefficient of z to the power n in that function. Okay? How to get that? Right? For a function, if you want a Taylor expansion, if you need nth coefficient, how to get that? differentiate many times. That is one way. Any other way? Kochi, if there is any contour integrals or something, if it reminds you anything. Okay, so there are formulas. One thing is that, right, you dz, so this is same thing as 1 by n factorial. Please dn, just let me know, dn by dz to the dzn and gz. Okay, so this is one way to calculate. It's true, right? This is right, differentiate it many times and put z equal to 0. Because there are this coefficient, if you differentiate z to the power n times, you have n factorial, and which cancels that, and other terms which will be some factor of z, if you put z equal to 0, it's kind of done. You get the coefficient in your hand. So this is very simple. Other way to do it, this one is same as, I'm just writing very small one. This is you can do it gz divided by z to the power n plus 1, in just a contour integral. Okay, so this will come out, the nth coefficient will come out as a pole, 2 pi I. Okay, so that will come out as a pole. Okay, so that's another way you can calculate it. This is sometimes harder, this is sometimes easy. It's mostly this is easier. Second one, because it's just one integral, and that one is n differentiations. Okay. Okay, so I still have this question: what is the 47th Fibonacci number? Right? No, I just want a formula, just expression, close. I want people to find gz and try to find out if you can find what is 47, nth Fibonacci number. Just write at least in some formula or whatever. Okay, so what we do is that this one tells us that this is general formalism. If you do not know Fn in some situations, it is good to use a generating function to calculate it. Okay. But in StatMech we do little more task, like little more, and that we discuss little more. I think these are important than what is the relation between generative function and that. I think that's more important than this non-equilibrium, and probably I'll illustrate little bit of that, then this conversation will be, yeah. Okay, done. Questions if you have any, or we do it in the last class.
This 3 decimal places, the answer to your question will be 2.61 or 1.61. 47th you wanted.
2 point something?
1 point, I forgot.
Would be very large.
Yeah, raised to n.
No. 2.2161. No. Yeah. Golden ratio to the power n. Yeah. Oh, there is another way of doing it. No, there are many ways of doing it.
Choose this as the recurrence relation. These are recurrent relations. So one can take any recurrence